At this point, we've developed a number of models of cell behavior. We, in Chapter 2, looked at empirical modeling or equivalent circuit modeling and found that could predict the voltage of a cell quite well if we knew the input current, but it was not able to predict the internal variables of the cell. Since those are important for some applications, for example, for next generation battery management and controls to prevent aging or to slow down aging at least, we started looking at physics models. And in Chapter 3, we looked at the microscale, particle scale models and found that those described homogeneous materials very well, but they were far too complex to implement in a real-time application. In Chapter 4, we saw how to do volume averaging over small volumes inside of the electrodes to come up with continuum scale partial differential equations, which were substantially simpler in a computational sense and still quite accurate, but still these are too complicated for many real-time applications. These models that we developed in Chapter 4 are infinite dimensional. So for every point in time, there's an infinite number of x dimension variables to solve for and an infinite number of r dimension variables to solve for. We introduced a finite element method solver called COMSOL, which approximates these infinite dimensional solutions using a grid of finite elements. However, to do very good solutions with finite element solvers, you still need hundreds of dimensions of points that you solve for. Now we begin looking at our final scale of model in this course, and we are again going to develop a cell scale model, and they're going to be built out of ordinary difference equations, much the same way the empirical models were. But these cell scale models are physics-based. They will retain all of the physics variables such that we'll still be able to simulate electrolyte and solid concentration and electrolyte and solid potentials and the Butler-Volmer flux at any point in the cell that we wish, as well as cell voltage. And we will be able to do this with a low order ordinary differential equation or set of differential equations. And this will give us physics-based predictions, which arguably are better, or can be certainly a lot better for many applications. The process of coming up with these cell scale ordinary difference equations involves some material that is probably new to most of you, and so we're going to develop it over 2 chapters of notes instead of just a single chapter. The first thing that we're going to do is we're going to introduce to you the form of the final model equations. And we actually saw this form once before. We didn't dwell on it too much, but in the equivalent circuit model, when we brought all of the terms together and talked about the enhanced self-correcting model, we put that model in a matrix vector form. And that form has a name. It's called a state space model. We're going to look at that again a little bit more formally this time, but still not in a huge amount of depth. It's an immense topic area, the state space modeling, and we teach courses on multivariable control systems 1 and 2 are devoted to understanding and applying the state space model to a control systems application, for example. Here we're going to really spend only about 2 lecture segments describing the most important aspects of this for our purposes before beginning to apply it. Also in this chapter, we are going to introduce a way to convert a frequency domain transfer function into a state space form, because that's going to be absolutely necessary. Once we know how to do that, in the next chapter we're going to look at how to find the frequency domain transfer functions of all the variables of interest, put everything together, and come up with our cell scale ordinary difference equations. So we said all of this. We desire to create cell scale ODEs that retain the fidelity of the continuum scale PDEs, but reduce the order to some small finite order. And instead of having hundreds of dimensions, hundreds of variables to solve for like the finite element method, we'll have on the order of a fifth order system, around a fifth order system when we're done, which is very similar to what we saw for our equivalent circuit models. So in this chapter again we introduce state space models, and we preview the approach used to generate a state space model from the partial differential equations. We start by generating transfer functions for each PDE. We'll do an example one here that's important for what we do next chapter, but the focus of creating the transfer functions is delayed until next chapter. And then we introduce and use something called a discrete time realization algorithm, or DRA, to convert these transfer functions to a state space form. So let's get started. A quick introduction to state space models. A transfer function is something that I hope you've seen before in some course. I certainly hope that you have seen Laplace domain transfer functions, and I'm sure you have in at least a differential equations course, but almost certainly in a circuits course as well, and maybe even some others. You may or may not have seen a discrete time transfer function in the variable z instead of the variable s, which is used in Laplace. The discrete time transfer function as a variable of z is not critical. It will be helpful to know that when we go through this section, but in fact the s domain is much more important, as we will see next chapter, and actually in this chapter as well to some extent. A transfer function is something that says if I know the input to the system and I know the transfer function, I can predict the output from that system. And in this schematic picture, I'm mixing up time domain and frequency domain, which is pretty common, but don't be confused. This is saying I have a time domain signal u of k, which is the input to a system which has an impulse response, discrete time g of k. It also has a transfer function, which is the z transform of that impulse response. In any case, that system produces a time domain output signal, y of k. The main point here is that transfer function tells you how a system converts the input to the output, but it gives you absolutely no information regarding what is happening inside of that system. There's no internal variables computation. It's input-output mapping only. State space models can provide access to what is happening inside the system, and that is critical to us because we would like to know what is happening to the concentrations and potentials and everything else, and those are internal variables to be sure. What's going on inside the system is a kind of loose way to talk about something that we can talk about a little bit more formally as the state of a system. And a state is an abstract quantity. It doesn't have only one definition for any particular system. There's many ways, as we'll see, to represent the state of a system. But in some abstract way, the internal state of a system at some time, k0, is the minimum amount of information at that time that stores whatever happened in the past. Basically, it summarizes the past such that if I have the state at time k0 and I have the input for future times, I can determine, predict, calculate the output of the system for all k bigger than k0. So the state, if you've taken courses that talk about state machines, it's kind of the same idea, except it's a continuous concept here. The state summarizes the past. So how I got to that state is of no importance. If I know that I am in a particular state, then I can propagate that state forward into the future with the input and compute the output from the state and the input only. A state space model describes a system's dynamics using two equations. The first equation is called the state equation, or sometimes the process equation, and it describes how the input influences the state and how the state then basically summarizes the input over time. And then there's a second equation that is called the output equation, or sometimes the measurement equation, describes how the state of the system and the input to the system both directly influence the output. A discrete time, linear time invariant state space model has this particular form here. X is the state of the system. In a discrete time, we can talk about xk plus 1 being the next value of this state. And we can write it as a matrix A multiplying the present value of the state added to a matrix B times the present value of the input. So this is a recursive calculation that updates the state at every time step based on what is the future state? Well, it depends on the present state and the present input. So when I get to the next time step, I have that prediction of the future state, which would be the present state then. The output equation says y are the output variables, is equal to a matrix C times the present state added to a matrix D times the present input. The output equation is memoryless. It's an instantaneous function. Notice that y, x, and u are all referencing the same point in time, whereas the state equation is a recursive equation that has memory because it, when looking forward, I'm using the present quantities, or equivalently, I could even write this, if you wish, x of k equals a times x of k minus 1 plus b times uk minus 1. I'm sure we'll see both forms because both are equivalent. K is a relative time index. In the equation, we implement it as an absolute time index. But this second form says, oh, the present state is a recursive function of the past state and the past input. In this equation, x is a vector, u is possibly a vector, y is possibly a vector. So we represent this here. That says that u belongs to r to the m, means that it's a real valued vector with m components. So it's m by 1, m tall, 1 wide. Y is a real valued vector that's p by 1. It's p tall, 1 wide. And x is a real valued vector that's n by 1. It's n tall and 1 wide. The dimensions that we have to have then for the other things, a is n by n, b is going to be n by, what was um, c is going to be p by n, and d is p by 1, p by not 1, p by, what is um. For our models, the way we describe them in this course at least, we have a single input U. U is going to be the applied current to the cell. So while U could be a vector in everything we talk about, it's actually going to be a scalar quantity, so P equals 1 for our models. But X is in fact a vector, and Y is in fact a vector as well, which might be surprising because we would expect the output to be voltage, which is a scalar quantity, but in fact we are going to be able to compute many outputs, including, as already hinted at, the concentrations and potentials and fluxes at any point in the cell that we want, and so therefore y can have multiple values. In fact, when we get to next chapter, we'll find that there are some subtleties involved in computing voltage that require y to have multiple outputs, but we'll defer that discussion until then. In any case, this is what we call the state space form, very important form. The only difference between two different systems that are both modeled in state space form are the dimensions of the state, and I suppose also the dimensions of the input and output vectors, and the A, B, C, and D matrices. I can infer, as we saw with our dimensioning of our A, B, C, and D matrices, if I am given an A matrix, I know N. If I'm given a B matrix, I know M. And if I'm given a C or a D matrix, I know P. So really, this different N is a bit redundant. If I know the A, B, C, and D, I also know the dimensions of the inputs and the outputs and the internals. So really, different state space systems have, the only difference is different A, B, C, D matrices. It can be helpful to use a block diagram to visualize how the model is operating. This block diagram is something that you could implement directly in Simulink if you desired to do that, and if you understand Simulink. The Z inverse block simply means unit delay. So the input to the block is delayed by one time sample to get to the output. And if xk plus 1 is a future state, then xk is the present state, then the delay of the future becomes the present. So the input to this delay block is xk plus 1, and we see that it is computed as a times xk plus b times uk in this diagram, and that's what the state space form says. Also, the output yk is equal to c times xk plus d times uk. So a simple diagram that actually can be used in simulation software to simulate a state space form, and we'll also look at MATLAB code that can do that as well. In order to help us see how we might build up a state space form by hand, let's look at this example here. Now, this example does assume that you have some knowledge of the Z transform. That's probably not absolutely necessary. I think we could find a way to do the example without the Z transform, but this is how we did choose to do it in this case. If you don't have knowledge of the Z transform, then you can scan through this section and get the general idea. The main point of this is that we can take a difference equation and write it in a state space form, and then we'll also see in the next section that we can take a state space form and write it in a difference equation. So there's a way to go back and forth between the two different forms. Also, we'll see that the state space form is not unique, and there's ways to transfer from one state space realization of a system to an alternate state space realization of the same system. These are the most critical concepts before we can really delve into the material of this chapter. So if you will, why don't you follow through this example to the best of your ability, and hopefully it will be illustrative to you. We start out this example with a single input, single output difference equation that is fairly generic, except that in this case I've done a third order system. The highest or the longest delay is a delay of 3 in this model. It can be generalized very easily to higher orders. There's really no challenge to doing that except for the amount of space it takes up when you're writing things out, so I decided to cut it off at 3. In order to make the transformation from discrete to the difference equation form to the state space form, I chose to take a transform of both sides of this equation term by term. And when I do that, the y of k becomes y of z. The a1, y of k minus 1 becomes a1z inverse y of z. Because there's a theorem about z transforms that a unit delay in the time domain is equivalent to multiplying by z inverse in the frequency domain. And if you're really up to speed on your z transforms, you'll say, but wait a minute, there's also an additional factor that has to do with the initial output of the system, the initial value of that signal. But whenever we're finding transfer functions, and this is critical, we assume that the initial conditions are 0. So I don't need to worry about that, and that's simply because I'm finding a transfer function. So I can write that, and then I can write a2, there's 2 delays, so this is z to the power negative 2 times y of z plus a3, 3 delays, z to the minus 3. Y of z equals b1, that's going to be z inverse, u of z plus b2, z to the minus 2 power, u of z plus b3, z to the minus 3, u of z. What the z transform has done is it has converted a difference equation in time into an algebraic equation in frequency. Notice the left-hand side has a common factor of y of z that I can factor out, and the right-hand side has a common factor of u of z that I can factor out. And when we do that and divide through, and in fact multiply both sides by z to the plus 3 over z to the plus, so we can do z to the plus 3 times that side equals that side times z to the plus 3 to get rid of the negative exponents. We get this transfer function here. So that's g of z. Once I have this transfer function, the numerator part of the transfer function has what we call the zeros of the system if I factor it. The denominator has what we call the poles of the system if I factor it. So I'm going to factor this system into a certain way that I can write g of z equals, well, let's do the zeros first, or last rather, and then we have numerator times 1 over denominator, and that means we can call that gn, we can call that gp, or I have y of z then is equal to the numerator times 1 over denominator times u of z. That's really what's happening. So we apply the denominator to the signal first, apply the poles first, and then we apply the numerator to the result, and we get the output. Here is the denominator, the poles of the system, and we create an intermediate result that we call v of z, where v is what I get when I take the input u and I put it through the poles, but I don't put it through the zeros yet. And that is that transfer function. And with that transfer function, I can unwrap it. Again, I get a difference equation back, and here is that difference equation. So vk plus 3 plus a1 vk plus 2 plus a2 vk plus 1 plus a3 vk is uk. Now this is not voltage, this is just some generic variable v that is our intermediate variable for this example. Converting this difference equation to a state space form, I will have many choices for how we define this state. this is one choice here, but there are actually an infinite number of equally valid choices, and as long as we're consistent, it doesn't actually matter what we choose. So I have decided to choose this to be the state. So it's written as a row vector with a transpose, so it's really a column vector. I wrote it as a row vector to save a little bit of space. If that is x of k, then x of k plus 1 then is this. Just add 1 to the k in there, so it becomes vk plus 3, then plus 2, then plus 1. And looking at this expression, I can move all of that over to this side and get an equation for vk plus 3. So vk plus 3 is equal to minus a1 vk plus 2 minus a2 vk plus 1 and minus a3 vk when all that stuff is brought over to the right side. And then don't forget that, plus 1 times uk. Then in my form, because of the way the form works, I have to figure out equations for vk plus 2 and vk plus 1 in terms of the prior state vector and input. And these are almost placeholder equations because you see that vk plus 2 is 1 times vk plus 2, vk plus 1 is 1 times vk plus 1, both of them 0 times uk. But this is important because, as I said, the definition of the state is arbitrary. I actually have to have these equations in there in order for the state space form to have a fixed result. There is our state equation. Now we can talk about the zeros of the system. G of z is equal to the numerator, we call that gn in our scribble up above, times gp, which means that y of z equals gn times gp times u of z, but all of that was called v, so it's gn of z times v of z, and that's then gn and times v of z. In understanding that the z inverse is a unit delay and z to the plus 1 is a unit advance, y of k then is b1 times vk plus 2 and b2 times vk plus 1, and b3 times vk is what that means. And in summary, we already found this, but now we have this equation here that y is b1, the first state was vk plus 2, b2, the second state was vk plus 1, and b3 vk, that was the third state. There is our state space model for this difference equation. So any equation that has that form with different a values and b values, I can just plug in those a and b values into the state space form, and I have a representation of it. There are lots and lots of equally valid state space models for this transfer function, and we're going to see how they are related in the next section. One very, very simple thing to notice was that I defined the state here as vk plus 2, vk plus 1, vk. That was the definition of the state. But I could have come up with a set of equations that instead did vk plus 1, vk plus 2. There's no reason why I couldn't organize things differently, but that would give me different ABCD matrices. Or I could shuffle them, or I could do linear combinations of them, and so forth, and that would just give me different ABCD matrices. We'll see about that in the next section. A lot of discrete time transfer functions are not strictly proper. By that I mean that the order of the numerator of the transfer function, it could actually be equal to the order of the denominator. In this example, we had the order of the numerator less than, which made it a little easier to go through. But if we have a transfer function that is not strictly proper, then what we do is we do polynomial long division. So if I had g of z equals b0, z cubed plus b1, z squared plus b2, z plus b3 over z cubed plus a1, z squared plus a2, z plus a3. If I had that with this kind of a term, we would have to perform polynomial long division of numerator by denominator and get, oh, that's equal to b0 plus a new numerator over the same denominator, z cubed. And this new numerator would be what we used in the process to find the state space form, and this B0 turns out to be the D matrix. So there's a process that's involved. Not going to worry about it too much because the methods we develop take care of this automatically, so we don't have to do this manually. And finally, there is a MATLAB command that converts a transfer function, a discrete time transfer function, into a state space form. If I give it the numerator coefficients of the transfer function, the denominator coefficients, and a sample rate, then it will give me the ABCD matrices automatically, and that's pretty nice. So we're off to the races. We have an introduction to the form of a state space system. We have a quick example of how to convert something like a difference equation, which might be more familiar to you, into a state space form. We'll have one more section on working the other way around to convert a state space back into a transfer function to get a little bit more experience with these state space forms. And that's what we do next.